All right, it should be broadcasting down to the coast now, is that right? Okay, so today we're going to talk about Raster. And I, in the past, have taught this as two, as a single lecture. Today, we're going to divide this up into two. We're only going to talk about Raster today, and then we'll talk about terrain next week. So the file is all together, but we'll stop it partway through. It only looks like there's like 30-something slides, but I'm also going to supplement that with some examples in ArcGIS. Next week, we'll get started. We'll talk about terrain analysis. Then also, another thing I put up here, this is another PDF file, and I'll explain that at the end of what we talk about today. Basically, there's some examples of things that might be test-like questions. That's what this raster problem helps is. So start off with the raster and terrain analysis slideshow. All right. So we're going to start off with a review. Raster, we've worked with them in a few labs now. It's different than vector. Basically, some people might call it an image. But with an image, usually it implies that we're storing reflected visible light back toward our eyes. And really, with the raster, we can store any data. We can store data that's of a nominal scale, ordinal scale, or an interval ratio scale. And I've got some examples of that. That's what I mean by that. Okay, so I have a few sets of data here. I don't know if I have a folder connection to my D drive here. I've brought a few data sets with me. I'm going to have to put this over there and drag these on. So this this isn't something that you have access to, but some data I want to show. Okay. So we've got some content here in this LB, which stands for Laguna Beach folder. So this is near where I grew up. All right. So I've got a data set here. Actually, the first thing I'm going to do, I'll drag one of these data sets on. We've used this type of data. what's another word, a generic term, for this type of raster data set that represents elevation? Digital elevation model. It's a model of the elevation. Okay? So every cell in this raster represents elevation, the height above some datum, some vertical datum. Sometimes it's sea level. This other raster that I just brought up is actually stored in the cloud, and I don't have access to the raw values of this raster. It's stored in the cloud for anybody to use. It's a global imagery data set. Just kind of give you a reference. This is in Southern California, and this is a high school down here. This is a junior high school up here, and just off the map there's an elementary school. The beach is over here. And so you can see that the elevation data set kind of makes sense. You can see this ridge line, this ridge line. These are basically canyons, little canyons. This one goes all the way up into Orange Canyon. These are little canyons. We can tell that they're canyons because here dark means it's low, bright means it's higher, relatively speaking. We can change the way it's symbolized, make it look more like an elevation map that you might see. On a map. Here's an example of doing that. So now, the very lightest blue colors here represent the lowest elevation, and you go all the way up into the frozen peaks of Laguna Beach. It's white. No, it doesn't mean that it's cold up there. It's just that we've chosen to symbolize the very highest values, which are what? 295. What do you think that's in, by the way? It is feet above sea level. What's the feet above sea level where we are right here? I don't know exactly what it is, but it's within 20 feet of this. It's in the low 300s. Interestingly, here we're talking about a distance of less than a mile. We've already climbed up into 300, whereas our physical landscape is a lot different here. Okay? We're in the coastal plain, yeah, and it's we're a little less than 100 miles away from the ocean. But here we've got some big mountains, not big mountains, really kind of small mountains. It's funny, my nephews and nieces go to this elementary school up here. It's called Top of the World Elementary School. But you can see back into Orange County. That's where I grew up. But anyway, yeah, we've got quite often. That's one reason why I chose to use this rather than something around here, because it wouldn't have been of a big difference to show elevation data. Okay, so that's a raster. We zoom like way in here, and we can see the individual cells. So the individual cells there. That's a house, but then when this pops up, you can see the individual cells. In fact, the imagery data set is a raster, and it has individual cells, and those cells are smaller. The raster resolution of that data set is smaller. We can zoom in. I don't know exactly what it is, because again, it's not stored on my disk here. That's stored in the cloud. But we can get the elevation anywhere in this map. Press back too many times. Just by clicking I. So the elevation on at that cell is 137 feet above sea level, and some change. So here, the raster, the values that are stored are elevation. That's not on a nominal or an ordinal scale. That's on an interval ratio scale. In other words, it's a real number that represents an actual value. The difference between interval and ratio being that one represents an actual quantity. You can have 0 precipitation. This is not a precipitation. But you can't have 0, you can have 0 elevation, but what does it mean? It doesn't mean that the elevation doesn't exist at that point. It means that you're at the base, the 0 line. In either case, the reason why we group them together, integral ratio, is that they're both real numbers. We can say that if this cell is 136 and this cell is 134, how many feet are we going down as we travel from the middle of that cell to the middle of that cell? 36 and 34, 2. We're going down 2 feet when we travel between those two cells. And those are real numbers. Okay? That's in contrast to a data set like this. Well, actually, I'm going to zoom back out. Zoom to layer. Okay, a data set like this. This data set's much more coarse. That's why I zoomed out. This is land cover. Land cover data set. It's more coarse. It's taken from 30-meter satellite imagery. So each cell represents 30 meters. And the value in the cells represent the land cover at that point. Okay? Now, if we look at the elevation data set, we right-click on it, and we try to open up the attribute table, it's all grayed out. Okay? ArcGIS recognizes that there are just so many values in that table that there's no possible way that you'd want to assign a different value to each table. That meant, basically, it knows that the numbers mean that they're real numbers because there's so many different numbers. In this data set, in the land cover data set, if you go to right-click on it, open attribute table is not grayed out. Okay? That's because there's only, let's see, maybe a handful of different values. And these are the meaning of those different values. So it has an attribute, a table associated with it. So one of the things that we learn here is that attribute tables are not purely just for vector data. Okay? This is an example of storing a data set that represents land cover in a raster format where the raster data has attributes. And just like with a vector data set, we could, like, let's say we got highlight. We're interested in where are the scrub shrub areas. Scrub shrub is a pretty common land cover, not developed land cover in Southern California. So if we choose scrub shrub, all of these light blue areas, those are the selected areas. Okay? Those are the areas that are in this category. They have a raster value of 12. In other words, the number that's stored in this cell here, in this cell, in this cell, all the cells that are right now light blue, is a value of 12. And all this, let's look at the mixed forest. Next one up. Not as many of them. There's only 300. There's only 395 mixed forests. There's a little over 1,000 scrub shrub. So there's the mixed forest. Mixed forest means that they're actually trees, and that some of them are evergreen trees, some of them are deciduous trees. So that's what those are. Okay? So those are 11. So I'm going to explain why this data set is different than the elevation data set. One of the reasons that it's different is that if you travel from the center of this cell, which has a value of 12, to the center of this cell that has a value of 11, the difference is 1. Okay? But the difference 1 doesn't mean anything. It just means that you traveled from some area that was mixed forest, scrub shrub, into mixed forest. So this data set is categorical or nominal. I don't have an example of an ordinal level data set, but if we had high, medium, and low values, that's how ordinal works. So we can look at any of the data sets here, or any of the open area, the classes. So here's developed low, which is the next, actually, that's the most common common, there's more of these than any others. There's 1,099 cells that represent developed low. What do you suppose developed low means? We could look up the metadata for a description, but we've got a developed high, developed medium, developed low, and developed open space. What do you suppose those mean?
Can it deal with whether it has levels of construction, like whether there's maybe 2 or 3 houses in the area, or 3 or 4 houses?
Yeah. Yeah, exactly. It's the density of the development. Most of these areas that are marked developed low, I'm going to zoom in here. So here's a big area marked developed low. I'm going to go ahead and turn off the elevation and then turn off the land cover. And we can see that a developed low area looks like a bunch of houses. Now around here, we probably wouldn't call this low density, right? That looks like there's like 2 or 3 feet in between each house. Okay, but where I grew up, we could sit down for dinner and look out our window, and the other people were sitting down for dinner, not like 10 feet away. It's just the way it was. Okay, in Orange County.
So really, it'd be more saying that developed low would be housing here, and medium would probably be industrial, and high would probably be.
Right. Low. If you go read the description, which I didn't pull up, low means single-family detached housing, basically. And then medium can be either basically apartment buildings or. So let's see if we can find any medium areas here real quick. Apartment buildings or something else. Look, this is medium right here. Okay, and this is something going on. I don't know exactly what it is, but it's bigger than houses. And then, it's not perfect. It's much coarser resolution, but even this area has been categorized. See if you can find any high areas. I think there's only a few. Laguna Beach is actually one of the last kind of bastions of a little bit less developed area than most of Orange County, particularly the canyon. Yeah, this is like downtown right by the beach. But they're calling this high density. It looks to me like these are actually like either strip malls or stores because of the parking with outline. In any case, that's a raster data set, and this type of raster data set that's holding discrete data or nominal data like this, zoom to layer, is the most like vector data, points on the polygon. We could actually convert these into polygons and convert them back without really losing any information if we wanted to. We could store the coordinates of this polygon here, the boundary of each polygon. Move it back and forth between the raster and vector data model. All right. Selection, clear selected features. There's a few other data sets in here. This is actually the data that we use for a lab in the Raster GIS course. Here is a data set that represents the intensity of the vegetation. NDVI stands for Normalized Difference Vegetation Index. So here you can see the intensely vegetated areas are bright. Things that don't have vegetation or any vegetation show up dark. So most of the roofs in this area, well, like here, we have lots of asphalt roofs. Actually, a lot of these is pea gravel and flat roofs. My dad lives somewhere on one of these streets, and then the asphalt on the road is again not vegetated. And this area right here, let's see what's over here. Oh, this looks just like an area that's in the upland. This area right here is what I'm referring to. An upland area that's on the top of a ridge line, so it probably doesn't get as much water. The water does get immediately flows off, and so it's bald. Whereas down here in the bottom of the canyon is where most of the water goes to, and so that's where you do get some vegetation, and that vegetation is what shows up in this color.
So like bald is in grass or bald is in there?
Yeah, I mean, most of the time it's dead grass.
Okay.
So the way it works around here is in April. It rains. It does rain in Southern California most often in the winter. And so up until January, February, March, April, these will be kind of green. They'll green all the way up, and in April, rain stops. It gets really dry, and everything's dry all the way through. And then in actually this time of year, October and November, we get really dry winds. I think we get, I haven't been there for 20 years, but we get really dry winds that really kill everything off. And so it's peak brownness right now. And actually, you probably heard in the news that this often leads to fires, and this is one of the years where they are getting lots of fires. Okay, so in this case of the NDVI values, we also have values, but in this case they range from from -1 to 1. So different data sets can have different domains. Just like a vector data set can have multiple attributes. With the raster data set, you have multiple raster layers to store all of your attributes. So each cell here, we have an attribute that's the NDVI value, we have an attribute that's the elevation, we have an attribute that's the land cover class. We can have lots of different attributes. Those are the three I've shown. But really, with a raster data set, most often, for every raster, for every attribute, you have a different raster layer for that attribute. All right. So that's a review on what raster data sets are. We can do things with raster data sets to build kind of complex constructs. A little easier to do with vector data, but for problems that actually are purely based on proximity, which lots of elevation problems are like that, like where's the water going to flow type of problems, we can take nearby cells and connect them up into networks. In other words, we could say, for a particular elevation data set, where's the water going to flow out of every cell? Which direction is the water going to flow out of every cell? Because we know that that's based on physics and science. The water typically flows in the direction of the steepest downward flow. So if we have a model of the elevation, we have to find out which direction is the steepest change, and we can model water flow out of that cell. And then we can model water flow out of every cell. We have a network, and we can say, okay, well, now we know that if we drop water here, we can follow the path that it will take out to the ocean. In this case, we have the ocean pretty close by. Some other examples, we could predict the fate of pollutants in the atmosphere, the spread of disease, animal migrations, crop yield. I just showed you that NDVI layer. If that was crops instead of shrub, we could use it to predict crop yield. Various other things that we could do with that data. Just making sure I started the recording. Okay, you've already noticed this if you've done some of the labs, but anytime you execute a raster analysis tool, that's what we're talking about today, is raster analysis, it requires a special license. And so you have to go up under here and say customize extensions and turn on the license that's associated with doing raster analysis, and it's called spatial analysis. Turn on spatial analysis. The spatial analysis license, the retail price for the spatial analysis license, is actually almost as much as the ArcGIS software is. So it's over $1,000 for the the non-educational retail version. So it's expensive. But it does open up a lot of neat possibilities. Okay, let's kind of look at a little bit of history about doing raster analysis. It's actually begun back in the 70s. And since rasters are basically a bunch of numbers, most of the analysis involves combining numbers to give us the result that we want. A simple example of this would be if I have a raster that represents elevation in feet, but I want a raster that represents elevation in meters, I can take every cell and divide it by 0.3048, which is the conversion factor between meters and feet. And I would be converting my raster and creating a new raster where every cell represents the elevation in meters. Okay? So that's an example of a calculation that I'm doing to a raster. So that's the concept of map algebra. Manipulating these data sets that contain numbers and creating new data sets. And that's a simple example. We'll talk about more complex examples, but we do have a whole course on even more complex examples. That's 418. It's often being taught this. So cell-by-cell combinations of raster layers. Each number represents a value in a raster cell. We can do simple operations. Okay. We can also do more complex operations. We've got addition, subtraction, multiplication that you could think of. We could do any sort of things that you started to do with the field calculator. Or I could say, if the value equals this, then do this. But if the value doesn't equal that, do something else. So an application of that might be that we were trying to find a habitat. We knew that this certain animal lived between this elevation and this elevation, and it had to also have a certain amount of plants near it. So we have a raster that represented the plants and a raster that represented elevation, and we could use a function to derive the areas that those live in. So this is a simple example of doing raster multiplication. And this isn't like in math when you did matrix algebra or something, and you had to like multiply this way and that way. We're not talking about that. This is just a one-to-one multiplication process. So the same geographic location in every cell gets multiplied by the same geographic location in another cell. So this would be like 5 times 10. Well, actually, we're multiplying everything by 2. 5 times 2 equals 10. 7 times 2 equals 14. So this is like the conversion process that I just talked about. We could multiply everything by a single number, or we could, in this case, add one cell to another cell. I'm going to show you an example of this from the thing. Okay. So this is not necessarily a real example, but it could be. Okay. So I came up with this example before class. I'm going to turn off. No, I'm not. I'm going to turn fuel on. And then I'm going to turn on this other one. So these two data sets here represent 2 different ways of measuring the Earth. This one called Fuel 2 is actually a measure of how much volume there is. So like in heavily vegetated areas, there's going to be more. In flat areas, there's going to be less. So if I zoom back out to the layer, you notice, like in this baseball field, in the infield, there's hardly any volume because it's just flat dirt. In the outfield, maybe it's the off season. It looks like there's at least some stuff there on the ground. So the brighter the color, the more volume that there is, the more or things that the sensor interacted with. In this case, it was a radar sensor. So the volume there represents the volume of the grass, and it's less. But it's even less than some of these other areas. Like here we've got a lot of buildings, here we've got a lot of buildings, and here we've got a lot of healthy vegetation that it's interacting with. So that's why it's brighter in those areas. Right? This data set here is it's pretty much like the NDVI data set we talked about before. It has a few other modifications to it. But it represents healthy green vegetation in this data. And so this is a very, not a real world example. But let's say that we wanted to model a fire in this area. And we decided that the fuel, the amount of stuff that could burn, was going to be the product of these two layers. In reality, it would be more complex than that. But it's going to be actually, let's say the average of these two layers. The average value of fuel 1 and fuel 2 is going to be the actual amount of fuel that can be burned if we're going to try to model one of these forest fires out west. Well, we can do that in what's called the Raster calculator. We can do any mathematical equation. We could take fuel 1, and add it to fuel 2, and then divide the result by 2. Because that's how you calculate an average, right? You're not going to argue that, right? The average of two numbers is one number plus another number divided by 2. So if I go back to here, I'm kind of combining these two. Well, not combining, but I'm doing the same thing. I'm adding them, but I'm also dividing them by 2. So instead of just getting the sum, I'm going to get the average value between the two. So now if I hit OK, this is going to run through. I already did it once beforehand. That's the one that's called fuel. So this is the result here. And you can see this data set should look like it's kind of a compromise between the other two data sets because it's the average value. So for every cell, I'm getting the average of these two cells below it. So that's why this data set it's even brighter in these areas that are not only lots of volume, but also very bright. And in the baseball field, which was over here, it's kind of darker. It's still a little bit brighter on the outfield grass, and so on. So that's calculating the average between two data sets. We could really do any mathematical function. If we had a data set that represented precipitation for every day of the year, we could come up with the average precipitation for every single pixel for the day of the year. We take all of the data sets, add them all up, and divide by 365 instead of by 2. When you do raster analysis, one thing that you have to watch out for, or that you have to think about, is that sometimes your cells don't line up. For example, our land cover data set that I just showed you has much larger cells than the elevation data set. It has smaller cells. So this could be like the land cover data set. This could be like the elevation data set. So ArcGIS and many other GIS software packages will actually take care of this for you if you want it. Well, not if you want it. You just have to watch out because it will take care of it for you. What it does is it always uses the larger cell size, ArcGIS will, always use the larger cell size, and for the smaller cell size, it'll actually take the cell that's closest to the center of this larger cell size. So to combine two rasters, you might think, oh, it's going to average all of these cells. No, it doesn't do that. It takes the cell that's closest to the middle and does whatever. If you told it to subtract the two layers, it subtracts this cell from this other cell. And So the output will always be the bigger of the two rasters by default. That is kind of to help you from making a bad assumption, because your data is only as good as the lowest spatial resolution. However, if you did want it to use the smaller spatial resolution, you would have to explicitly tell it to do that. That's done through, so anytime you run a tool, you can go down here to environments and change lots of different things. But it's most important here in Raster. One of the things when you're doing Raster analysis, you can change the cell size. See how the default is maximum of inputs? You can change the cell size to the minimum of the inputs. That's one of the options. Minimum of inputs. You can change it to whatever you want, or you can change it to any of the data sets you currently have loaded. You can change it to be a different value. All right. Doing a value, making a change to a raster using a function on a cell-by-cell basis is referred to as a local operation. Last week we introduced that term. Local operations, remember last week we were saying, okay, let's calculate population density for every state. Remember that was an example of a local operation. That's because we're looking at every state individually and taking one attribute of that state, which is population, and another attribute of the state, which is area, and dividing it one by another to get population density. Similarly, with the raster, on a cell-by-cell basis, what if we had the number of people that lived in every cell? Okay? We had the number of people that lived in every cell, and we divided that number by the area of every cell, which now would be constant. With states, it's different. Every state has a different area. But if we divided it by by the area of that cell, we would get population density in the output raster. So that's a local operation, a cell-by-cell operation, or more general terms, a unit-by-unit operation. Neighborhood operations are special. They're the next type of operation. We're still going to go cell by cell, but rather than comparing them to some number, or a number in a different cell, a different data set, neighborhood operations calculate a function that's based on all the nearby cells. And the neighborhood can really be whatever you want it to be. The neighborhood could be a large area, or the neighborhood could be a small area. Oftentimes, neighborhoods are just a 3x3 window around the focus of the neighborhood, the brown one. Dark gray one. The most basic neighborhood operation that gets done a lot, these are called in here they're called neighborhood operations. So if we want to do like focal statistics, I'm going to do this to the NDVI. Okay. I'm going to do a rectangle of, I'll make it a little bit bigger just so it's more obvious. I'm going to do 7 by 7. So everywhere within a 7-meter radius, 7-cell radius, I'm going to calculate the mean and store the output in the value, in the output grid. So here I'm going to say OK, and it's going to go through I meant to say results. It's going to go through and calculate the focal statistics. I don't know why I didn't add it to the... Maybe I did add it to the display and it's just down here. Nope. I don't see it. Add to display. Maybe it doesn't like where I'm saving it. Processing results. I'll try running it again and save it to a different location. I'm going to save it in the same place I've been working, which is my D drive, new LB. I'm going to call this mean NDVI. I'll just add it manually then. Refresh. It's not even there. Huh. Try one more time. If it doesn't work, then there's something wrong with my computer. And we'll have to forego the example. Yeah, it's not saving it. But if it, I don't know why the output says it's being generated. But what it would do is it would calculate for every cell, it would calculate the average of all of the cells around it. Okay? And it has the effect of smoothing the grid. A global operation, what it does is it calculates a value based on all the other values in the grid. So finding the maximum value in a grid or the minimum value in a grid is an example of a global operation. All right, let's duplicate slide. Okay, so there are many different types of local functions. We're not going to talk about all of them, but really anything that you can find on a scientific calculator, you can do as a raster calculator. Abstract by default. I'm not going to read them all, but there's lots of different things that you could do to a data set. Okay. You can also do logical operations. In other words, you could say, if this data set has a value that's not 0, and this data set has a value of not 0, give me the result. So in cases where they're both not 0, we'll get a not 0 result. In cases where either one is 0 or both are 0, we get a 0. One thing to note is that when we're doing raster operations, anything that has a value of no data in either grid will get a value of no data as a result in the output grid. Here's an example of an OR operation. So in an OR operation, if either value is true, it will be true. So this one has a positive or a non-zero value, so the output is a non-zero value. These are useful in, coming up with masks and saying, okay, if the value is non-zero, it might represent areas that aren't water. So I want to see all the water areas. A not operator turns everything that was that was true, in other words, non-zero, and turns it false. Everything that was false, 0, and turns it into true. Literally, probably hundreds of different logical comparisons, Boolean operators that are available. Most of the things that we talked about last week with tables, you can do with individual raster cells. The thing is, with individual raster cells, the values are always actually storing numbers. Always numbers is what's actually stored. A conditional function, that's basically an if statement in this case. Go away. In this case, the conditional statement, con, it says if layer A is less than 3, then make the output layer B. If it's greater than 3, make the output layer C. This is an example of a conditional operator. Another condition that you can ask is it null? If it's null, change it. Change the value. In other words, if it's no data. So neighborhood operations work with moving windows. So, the moving window looks at the neighborhood and calculates something like a mean, median, or a standard deviation, some statistic that you specify for this neighborhood. You might be interested in finding out the average elevation in a certain area, well, in a certain neighborhood. You wanted to smooth out your data. Here are the different statistics. Know what mean, median, and minimum, and maximum mean. What is range? The range is for this particular cell window. What's the range? In other words, the difference between the highest and lowest values. That might give us an idea of how drastic the changes are inside the window. For example, if it's a bunch of elevation values, could find the areas that have really drastic changes in elevation. In other words, like cliffs, because they would have higher range values. Slope is an example of a neighborhood operation that we'll actually cover next week. So is aspect. Majority just finds the value that's most often repeated. So you might do something with majority on a data set like land cover. So let's say that you have a land cover data set, but you don't like how there are little teeny islands of one cell everywhere. You just think that it would be better cartographically to remove the small cells. You could run a majority filter, moving window that would actually say, okay, for this rectangle, what's the most often repeated value? And it would get rid of small anomalies and the result would have less variability to the data set. Yeah, sorry.
So, but it could be said that any small things that were random on there that might be.
Yeah, I mean it could be human error, or it could actually be the truth. Like let's say we had a developed open. One little box of developed open. It could represent a park, a really small park, but we might not want to show that level of detail cartographically to people. All right, this data set, this example is another slide from your book. It shows that this concept of a kernel really we can express everything in terms of these functions, but we can also express them mathematically in terms of a kernel. So one way to express a mathematical mean for 9 cells is to use a kernel where each of these values are multiplied by 1/9 and then added up. Really the same math, adding up and dividing by 9. But the advantage of expressing it as a kernel is that we could then use any kernel that we wanted to. We could change one of these kernels to multiply it by a slightly different value, and it would tell us something different. Okay? One kernel that gets used a lot is to have this value really high and all the surrounding values really low, or vice versa. And it will actually accentuate hits and spikes in the data if we're looking for things that are anomalies, things that are wrong, okay? Things that are errors or blunders. The only problem with this kernel model is on the edges you'll get different values. So ArcGIS actually takes care of this for you and knows to adjust these values differently. So in the corner, you get 1/4, and the margin you divide it by 1, multiply it by 1/6 instead of 1/9. Okay. But not every package does that, so you just have to keep that in mind. Sometimes you just throw out the edges, particularly if your data set is already a little bit, your extent is larger than your study area. It doesn't really matter what happens on the edges. But remember that doing neighborhood operations can affect the edges. All right. So here's a very simple kernel that just takes the cell to the, well, it depends on how you're looking at this, I guess. The cell to the east and multiplies it by 1, and the cell to the, I guess that would be the west. The cell to the west multiplies it by 1, and the cell to the east multiplies it by -1, and then adds up all the cells. It actually multiplies all the other cells by 0, but that's 0 times 8 equals 0. So basically, this is the kernel that you would give it if you just want to take the cell on the right and the cell on the left and subtract the difference. So the output is the difference between the cell on the east and the cell on the west. So this is the output. So this could be a good data set for discovering any north-south running features. This would be a good data set for discovering east-west features. So this concept of a kernel kind of opens up this whole field of digital image processing. So we could find things that are vertical, horizontal, left, right. We could find different textures. We could find all sorts of things. Even this has application even like things like computer vision, like seeing things. Okay? So if we could come up with a kernel that kind of identified eyeballs or something, we could do that. That's not really geography, but we could find a kernel that might identify different types of crops based on their texture and things like that. So we cover this a lot more in both 518 and the remote sensing courses. So we could do all sorts of things. Moving windows could be used with the mean kernel to smooth things out. They can be used to identify noise and actually either remove them or figure out where they're happening or why they're happening. Data sets that identify noise are referred to as high-pass filters. Okay, a high-pass filter works by taking pits and spikes and accentuating them. So you get an even bigger positive value or a bigger negative value. So here's an input layer with some noise. These are noisy values. They're a lot different than their surrounding areas. The kernel for a high-pass filter has negatives around the outside, and in the center, it has a positive value. And so what that has the effect of doing is multiplying the surrounding values all by -1, and the center value by 9, and finding the average, you get even higher spikes and pits. So this is what your output would look like. Your output, everything where the values don't change that much, stays close to 1 or 200. The areas that are significantly different have very high values if they're significantly positive, and very low negative values if they're significant, and they're pits basically. Okay. So here's a mean filter, which is just averaging the smooth layer. This is what I was trying to show you before. So the pits and the spikes get smoothed out a bit when you do that. Now, let's say that most of that applies to numbers. Every cell represents a number. Well, what if every cell has a number, but that number doesn't represent things like elevation or precipitation or temperature? What if they represent land cover, like the data set I showed you before? What if we have one data set that represents land cover in 1980 and another set that represents the land cover in 2015? That's an overlay problem now, right? I mean, if we just took the land cover and added them together or subtracted them together or whatever, we could kind of try to interpret it, and we would at least know, if the land cover categories were all the same, if we did a subtraction problem, 12 minus 12 in the scrub areas, 12 represents scrub in 1980, 12 represents scrub in 2000. If we did a subtraction problem, anything that was 0 would represent what? Anything where we subtracted the land cover from one year and the land cover another year, if we get a 0, nothing's changed exactly. But what do all the other numbers mean? If it was 1, does that mean that it changed from a 2 to a 3 or an 11 to a 12? Right? We wouldn't know. And we could do a change, no change, which would be useful. And so that would be an example of doing a cell-by-cell addition, and we would get some information, but we wouldn't get all the information that perhaps we wanted to. So there's some additional things that you need to think about when you're doing raster overlay. So first of all, let's talk about just raster clip. Really, there's no such thing as raster clip, because a raster is always a rectangle. But somebody always comes to me and says, I don't want these cell values because I'm just trying to get the cell values for my county or city. I don't want these cell values. How do I clip them out? Well, you can't clip a raster. What you can do is mask out the values you don't want. So what you're really doing is you're turning all these values that you don't want into no data. And sometimes you can make the raster a little bit smaller because you really only need that area right here. You only need this area. You don't need all the way out to here anymore. Okay? So clipping or masking out a raster, one way to do it is just multiply it by a ones and a zeros raster, where you multiply everything by 1 in the areas you want to keep, and you'll get the values, and you multiply everything by 0, and you'll get the 0 values. That's probably the most straightforward. You're not turning these into no data, you're turning them into zeros. If you actually wanted to turn them into no data, you'd have to do the conditional operator that we talked about before. You have to say, if in the clip raster it's false, turn it to no data. If it's true, assign the value from the input raster. You do a conditional operation. So that's the raster clip. Another function type that we didn't talk about was a zonal function. And a zonal function is kind of like another way to do overlay. A zonal function says, okay, I have either a raster or a vector data set that represents zones. These zones might represent different cities. Okay? Hattiesburg and Petal, we don't have too many other cities connected to us, but like in Orange County, we could have Irvine and Santa Ana and Costa Mesa, Newport Beach, and Laguna Beach. Each of these letters represents a different city. And this cell might represent, this grid might represent people. And we might want to know what is the, let's do elevation. This might represent elevation, and this represents cities. What's the average elevation in every city? Well, we run a zonal operation, and what it would do is it would take this, overlay it on this, and for every C value, it finds the average. So in these cells, these are all the ones with C's. It's better at this than I am. But it finds all the values with C's, and it calculates the average of all those values and stores the average value out there in the output layer. So you've answered the question, what's the average elevation in city C is 9.2. Okay, so it's the zonal average. The reason why I switched from people to elevation is the average people per cell. I guess that does make some sense. It's more like that's more like the population density. Okay? So anytime where you want to come up with the average amount of something that's in a raster by something else that's either in a this actually could be a feature class. It could be polygons. Okay? Then you use a zonal operation. So that's how you answer that type of question. And the output can be a raster, but actually more often it's a table. You know, it's more interesting for it to be a table, where the table says C 92, B 37, and so on. See if because it'd be nice to demonstrate this. Maybe it's, well, it didn't seem like it. I'm going to, I'm just going to see if I open and close it, if it'll fix my issue with the data sets. I did open it back up, didn't I? Okay, so I'm going to open up Untitled. I didn't name it anything interesting. And then what I'm going to do is I'm going to run this zonal operation. Zonal statistics does just what that slide said. Does this. Zonal statistics as table actually outputs it as a table. So what I'm going to do is I'm going to calculate the average elevation. Actually, maybe I'll do the average vegetation index. The average vegetation index by land cover. I'm going to take, for every land cover, I'm going to find out what the average vegetation index value is. Because it should be higher in vegetated areas than in lower of it than in non-vegetated areas. So we'll see if that's the case. So I'm going to call this LCNDVI for land cover by NDVI. Oh, now I get an error. Background server threw an exception. There's something wrong with my install here. I'll try to save it in a different location. Like maybe it's not coming off of that drive very well. Looks like it's at least running this time. Yep, okay, there it goes. So now I'm going to open up this attribute table, and it's going to give me that answer. So now, this value represents the raster value. I'll have to go in and remember which values are which. But I do remember that I think it was like 10, 11, and 12 were the forested, shrub, mixed, and forested areas. So look at the mean in those areas. In general, it is much higher than it is in all of these other areas. This one was low density residential. See how different it is? Way lower than well, actually, well, no, I said it was these three. So it's actually highest in, this is the wetland type. So that makes sense, because this is forested wetland. Let's see, let's make sure that I'm right. I think 13 is forested wetland. So if I right click and say open, yep, it's forested wetland. My guess is that that's actually a mistake, right? There's no forested wetland. Maybe there is, but even if it is a mistake, the reason that they made the mistake probably was that it showed that there was just so much vegetation there, and that was the cue to classify that as forested wetland in the first place. Because if trees were growing in an area where there's an abundant water supply, they're probably more healthy. Okay, so that's a zonal operation. Finding a statistic, a summary statistic based on a region or a zone is what the terminology is. All right. Okay. Now, let's get back to that thing where we're going to combine a land cover from 1980 from land cover from 2015. If we tried to add it, we get some ambiguous results. Or even if we try to subtract it, we get ambiguous results. Okay? So what if we want to get some unambiguous results? So, basically, this gets into the problem that we have. We don't have a one-to-one relationship between objects and attributes, too many cells. Oftentimes, it's better to convert it to vector. Okay? But if we want to, I'll go back to that other slide in a second. If we want to solve that problem, one thing that we could do is take the land cover back in 1980 and multiply it by 10 first, then add it. This only works if there's only one digit. And then the first digit represents 1980 and the second digit represents 2015. So anytime where there's 11, 22, 33, 44, those all represent areas where no land cover change occurred. In our data set, we might have to multiply 1 by 100 to get this to work right, because we have double-digit numbers. Okay? Our numbers go from 1 to 14 or something. So if we multiply it by 100, we could add them together. The first two digits would represent 1980. The second two digits would represent 2000. And then we could reclassify this as a from to table. All right. Now, in a vector data set, one last thing to talk about. In a vector data set, we have an attribute table that's always one-to-one, where for a particular raster, there's one row. Particular polygon, there's one row in the table. The raster I showed you with land cover, the thing that you need to realize is that there's still an individual cell, and each of those individual cells does not have a one-to-one relationship. It should be like a red X here. In the attribute table. That's not the way it works. The way it works in a raster is that for every raster value, there's one row in the table. And there's usually a column that tells you how many cells that represents. So that's what's happening in our land cover data set here. So we have one row in the table that represents multiple cells. And this column tells you how many cells it represents. So there's 401 cells that are developed median. In a polygon data set, one polygon represented by one row in the table. Now, one polygon can have multiple parts, but it's still a one-to-one relationship. All right, I think, yeah, so this just kind of talks about how when we just do an addition, it's ambiguous, we have to add 10 or maybe sometimes add 100 in order to get that proper output data set. All right, so that is as far as I wanted to get today. And before we go though, before we take the break, I told you that I wanted to mention this other file and kind of go through it, and then we'll take our break. And that's this file right here, Raster Problems Help. You open that up. This kind of, well, this kind of talks about, it says there will be questions about these on the test, all right? So there'll be simple operations on the test that have you add or maybe multiply two different rasters. You should be able to do this sort of thing. In this case, what would the result be here? 1 plus 3, this is plus. 1 plus 3 is 4. 4 plus 1 is 5. Easy, right? Multiplying, easy. You can do those sorts of things. Okay? The lab might make this a little bit easier to understand, but there's the answers for you, in case you were wondering. And then this is an example of a high-pass filter and a mean filter. So you can look through the book, but really easily. So on the test, we'll ask what's the value in just one or maybe two of the cells. So what would the value here be? The value here in that cell, that's this cell right here, it's the average for the mean. It's the average of all of these cells. So it would be 2 plus 2 plus 3 plus 2 plus 3 plus 3 plus 2 plus 4 plus 3 divided by 9. So that would be 8. This would be, what's 4 times 3? 12. That would be 20. 24. 24 divided by 9. So 24 ninths is what goes in there. I can't think of that number off the top of my head. But I added up all of these cells, and the output I got I took the average value. Okay, this one's a little bit different. I have to take each of these cells and multiply them by -1. Just think of all these numbers as negative. Add all those numbers up. So it would be 21 because, did I do my math right, by the way? This is 12, right? All these cells, 3, 3, 3, 3. That's 12. And then that's 8. That is 24. So this would be -21 around the outside. And this would be positive. 9 times 3 is what? What's that? 27. So positive 27 minus 21 would be the answer there. 27 minus 21 would be 6, right? Oh, and then you have to divide it by 9. So 6 divided by 9, that's the answer there. This is 24 ninths. That's the answer there. Okay? And then this is just a repeat of that other slide, but yeah, that shouldn't be in there. So we'll go through a couple more of these types of questions. Well, you'll see some on the lab, and then we'll go through a couple more when we do the test review. That's something to have there. All right. So let's go ahead and take our break. It's 2:20. We'll meet back at 2:35 and go over the lab. Before we leave, I'm just going to stop the video and I'm going to download the lab data because it's a little bit bigger. So there we go. I have to rename it. I forgot to rename it before.